Hey, let's talk about thermodynamics today for a minute. Thermodynamics is all about heat and temperature and how much work we can get out of that energy. Remember, we said heat is a form of energy. So let's take a look. There's some important stuff that we use every day because of this. Um, First thing I'd like to tell you about is temperature. There are lots of ways we can measure temperature. The one we're most familiar with in this country, of course, would be the Fahrenheit. So I'll start with that, I guess. We mark those off with water freezing and water boiling. Water would freeze at 32 degrees Fahrenheit, boil at 212. Those are important numbers if you're trying to figure out what the state of a material is or something. You know, if it's 20 degrees, chances are that's ice, right? And 110 would almost certainly be steam, depending on the pressure and all that. Um, but in science, we usually use the Celsius scale, which makes a little more sense. It goes from 0 to 100. Like everything else in the metric system, it just kind of makes more sense to say, well, water is the most common substance on Earth and pretty important to our life. So let's use that. Everybody has access to it. 0 would be water freezing, and the point where water boils is 100. Sometimes in thermodynamics, though, we need this other temperature scale called Kelvin. And in order to do that, all you have to do is add 273 to whatever the temperature is in Celsius. Okay, so you can see 100 plus 273 would be 373. So some of these numbers have to be done in Kelvin, and it's really easy to convert back and forth. No big deal, but that's that. Now, of course, if you want to convert from Celsius to Fahrenheit or Fahrenheit to Celsius, then you need one of the little formulas that you see up here. And you could just put in the temperature in Celsius. Let's say it's 100 degrees Celsius, right? So if I put 100 right there, 5 would go into 100. 20 times 9 would be 180. And then I'd still have to add 32, and I'd get to 212. All right, you could do that on the calculator too if you wanted to. But that 100 degrees Celsius turned into 212 Fahrenheit, and that's what we said right here, 100 degrees Celsius, same thing as 212 degrees Fahrenheit, like that. And the other formula would take you back the other way, okay? But the temperature scales are important. In science, we usually use Celsius. In thermodynamics especially, we often have to use Kelvin. So if I slip up and use that, that's what we're talking about. It's called an absolute temperature scale, and it goes down to absolute zero, where theoretically everything stops moving. But let's not worry about that right now. I'm going to tell you that all stuff, all matter, is made out of molecules. So here you can see molecules or atoms that are together. Materials could either be a solid, a liquid, or a gas. And these little animations do a pretty good job, I think, of illustrating what those three states of matter, phases of matter, would look like. A ice cube is going to be locked into shape. There's a little bit of vibration in the atoms and the molecules of the substance there, but they're not going anywhere. They're not sloshing around like the liquid is. They're not filling the whole room like the gas is. You can see the gas molecules are bouncing off the walls, bouncing off each other. The liquid kind of sloshes back and forth. It's going to, gravity's pulling it down and everything, whereas these guys have enough energy to where they're just flying free. Okay? So it's all the same stuff. I could take water and freeze it into an ice cube. I could let it melt into water, and then I could boil it into gas. And all I really have to do there is add heat. I could add heat. We'll put Q for heat there. Add heat to an ice cube, it's going to melt, and you've got liquid. Add heat to a liquid, and that'll turn it into a gas. Now, there's a couple ways that these things happen here. So let me tell you real quick about this. When we talk about the measurement of heat, here's the word metry, measurement. Calor means heat. So the measurement of heat is called calorimetry. And there are two kinds of heat that we principally need to think about. One is called sensible heat, and that means that we can sense it, that we can detect the temperature changing. Basically, I'm going to add heat and the temperature is going to go up. So you might have a problem that looks something like this. Find the energy needed to heat 4 kilograms of iron from 20 degrees to 47 degrees Celsius. If this number C, that's this constant right here, equals 448 joules per kilogram degree Celsius. Every material's got its own number right there, and you'd have to go look it up on a table. If I were to give you some of these problems, I would certainly give you that constant. You don't have to memorize them. You don't even really have to know how to look them up. Just be aware that copper is going to heat differently than glass and different than bronze and different than gold, and everything's got its own number, and that's what this number is. It's called a specific heat capacity. Sometimes you see it called the specific heat or the heat capacity. I think the full name, it's like when your mom gets mad at you and she uses your whole name. Specific heat capacity there would be that. But it's really easy to do. You just come in and say, the formula says Q equals M. That's the mass. And here the mass is 4 kilograms. Times C. That's that constant that we look up on the table. 448 joules per kilogram degree Celsius. And right here my temperature goes from 20 up to 47. That's an increase of 27 degrees Celsius. And you can see how much sense that formula makes. If I had more mass, then I'd have to add more heat. Or if it was harder to heat that particular metal or substance, then I'd need more heat. And if I wanted to change the temperature more, then I'd have to add more heat. So they're all linear like that. You just go 4 times 448 times 27, and you'd get this amount right here. Now this is in joules. Remember that a joule is not a tremendous amount of heat. It's actually a pretty tiny, or of heat or energy for that matter. But watch the units right here. The kilograms on top are going to cancel. The kilograms on the bottom, the degrees Celsius cancel right there. Nothing left but joules. So that's how much heat it would take to do that. And I think you'll agree that's pretty easy. You get the mass, you get the heat capacity, and you get that change of temperature, and you got it. Now the other kind's a little stranger. This is called latent heat. Latent means not seen, hidden heat. So if I've got a glass of water here and I stick a thermometer in there and I build a fire underneath the thing, it's going to start heating up that water, and I'll see the temperature rise on the thermometer. That's the sensible heat. That's when I add heat and the temperature goes up. But this is going to start to boil, right? And I don't see it go up anymore. It gets to 100 degrees Celsius with the sensible heat, and then it stops going up, and it just starts turning into steam. And so this is how much heat it takes to change the phase, the state of the substance right here. So, for example, in the problem here, find the energy needed to change 4 kilograms of iron from solid to liquid. We've got a chunk of iron, and we want to turn it into a liquid. We're going to melt it, right? Well, all you have to do is Q equals ml. So my heat would be the mass. Again, it's 4 kilograms. And then I'd multiply by this other constant. And once again, this is material dependent. Gold and copper and brass and glass are all going to have different numbers right there. So you got to go look it up on the table. And I would certainly give you those. Kilograms are going to cancel, nothing but joules left, and you're going to get about 1 million here. 4 times 247,000 is 988,000 joules, almost 1 million of heat that you'd have to put in to do that. Okay, that's calorimetry. I don't need you to go all crazy with that, but it's kind of neat to know and to think about how much heat does it take to change the temperature of a substance, how much heat does it take to change the state from a solid to a liquid or a liquid to a gas, and we can do that pretty easily. Some of those might have multiple steps. So if you wanted to take a chunk of ice and melt it and then heat the water and then boil the water, you'd have to jump back and forth several times and get all those steps in. That's what this picture tries to show right here. We're starting off with a chunk of ice at negative 20 degrees. So you can see that I'm having to heat the ice up to the melting point, 0 degrees. That's adding heat right there. That would be a sensible heat change. But then I have to add all of this heat, and I can't see a temperature change. It started at 0, it ends up at 0, but again, it started up solid chunk of ice, turns into liquid water. So I've added heat once, twice, I add some more heat, and that 0 degree water turns into 0 degree, into 100 degree water right there. And then I add some more heat all along here to boil it. I take that 100 degree water and turn it into 100 degree steam. And if I wanted to, I could heat the steam. I'd probably have to have it in a container holding on to it to keep adding heat to it, but whatever. So you could go through several steps of that, of adding a latent heat, a sensible heat, a latent heat, until you get to the condition you want. I don't think I'd ask you to do that, but you could see how that would be easily done, right? Now, when you heat things, they get bigger. So right here, I've got two ways. I thought I could get rid of that. This is called linear expansion. Thermal expansion is when you heat something and it gets bigger. So that's pretty straightforward. Thermal heat expansion, it increases. Here's an iron bar. They tell me it's 4 meters long. I'm heating this up by 80 degrees. And here's another constant that goes with iron. If I had glass rod, I'd have a different number there. If I had copper or anything else, I'd have a different number. And I'd go look up that number on a table. And again, I'd give you that. But you can see what's happening here. I start off with this rod, and I heat it up, and it gets a little bit longer. This delta L right there is the increase of length. So I'm looking at this formula, and I say the change in length is equal to that constant that they gave us, times the original length, times the change in temperature. And I don't have a whole lot of room here, but I think I can squeeze this in. Delta L equals alpha, that constant right there, 12 times 10 to the negative 6 per degree Celsius. It's not going to expand a whole lot, so that's a little bitty number. That's a 0.0000012. I gave you an extra zero there, sorry. The original length was 4 meters, and we went up by 80 degrees. Once again, you can see the degrees Celsius cancel there, and the meters cancel. I'm sorry, the meters stay there. So that's the unit that's left. This change in length is going to be in whatever units you started with. And I don't know that we've multiplied any scientific notation numbers like that. So let me do that. You could come in here, 12. That times 10 to the negative 6. The easiest way is with that EE right there. It's yellow, so I could go yellow, EE, and it just looks like that. And I've got a negative 6 for that exponent. And I go times 4 times 80. And there's how much it increased, 0.00384, not even 4 millimeters, okay? So it's not a huge expansion, but you do have to account for these things. I've got some pictures of train tracks where the sun was, it was a really hot day and the sun was shining on it. And when all that heat went into the train tracks, they expanded and got a little bit bigger and buckled up. They didn't have enough room, and the train tracks are all over the place and threw the train off the line and stuff. Okay, well, here's a second kind of thermal expansion, and this one is a volumetric. This was a straight line. The thing got a little bit longer. This one You start off with a cylinder or any kind of volume shape, and when you heat it, it gets bigger in 1, 2, 3 dimensions, right? So this is the linear expansion here, getting longer, but it also is going to get wider and thicker. So that would be the other kind right here. It's almost the same formula. We're talking about the original volume instead of the original length. We're talking about a change of volume instead of a change of length. And I've got this beta instead of alpha. So typically a table with materials would have 2 columns, one for the linear thermal expansion coefficient and one for the volumetric thermal expansion coefficient. All right, but you could come in here. This is the original volume. This is the beta. And if you'll notice here, these are both iron. Iron was 12 times 10 to the negative 6. Beta is alpha. Beta is 36 times 10 to the negative. It's usually 3 times higher for most materials, unless it's some kind of weird composite material or something. It's almost always 3 times the alpha over there, which is kind of interesting. It expands in 1, 2, 3 dimensions, and that's where that 3 comes in. That's a kind of long derivation to show, but you can do it if you like. So what we need to do here is the same old thing, and we'd simply have the change of volume is equal to beta, which is 36 times 10 to the negative 6 per degree Celsius. My original volume V naught was 40 cubic centimeters. I can put any units in here I like, and then it's going to come out those same units. I'm heating this by 80 degrees Celsius. Degrees Celsius are going to cancel. Nothing but those cubic centimeters there. You multiply those 3 numbers, and you've got the extra volume. That's not the total volume, but it's the new volume. I'm sorry. It is the expanded, it's how much bigger it is than what it started, if that makes sense. Okay? So those are kind of fun to do. Right here, there are different units you can measure heat in. We've been working in joules, and that would be the SI unit. That's the metric science unit that we like to use, and works out really nice. We can also use calories, which is the heat that it takes to raise 1 gram of water 1 degree Celsius. A lot of times we use kilocalories, which would be 1,000 of these. That would raise 1 kilogram of water 1 degree Celsius. And that one's important because that's the food calorie. When you look on a candy bar wrapper and it gives you the, this is 600 calories or something, you're eating that energy. It is heat energy. Your body is going to use that energy to keep itself warm and to run your brain and all the organs and to move your muscles. Those calories are important, but a kilocalorie is a lot of energy. You can see down here that 1,000 calories would be 1 kilocalorie, and that's 4,184 joules. So, you eat a candy bar, you need to go play tennis or run around the block or something. It's that much energy, and if you just keep putting that energy in without using it, conservation of energy says it's got to go somewhere, right? And it will. You can either put it into kinetic energy and move, ride your bike, or it'll go into potential energy, stored energy, and in terms of the body, that's going to be called fat. So kilocalories are kind of interesting. We call them calories. They're really kilocalories. Right here, the other one that you probably will see somewhere are British thermal units, or BTU. If you buy an air conditioner in this country, if you buy a fireplace insert, it's going to be measured in BTUs. That's how much heat it would take to raise 1 pound of water 1 degree Fahrenheit. You can see they're doing the same thing, but just not metric units right there. And that even gives you the way to convert. You could use any 2 of these pieces and convert back and forth. All right. Heat transfers 3 different ways, and we've got all 3 of them right here. Every time you put a pot on the stove, So right here's the eye of the stove, the burner of the stove. It gets hot, and when you set the pot down on that eye, there's physical contact there, and the molecules of the eye of the stove, of the burner, are vibrating, and they make the pot vibrate, and that makes the water vibrate, and that vibration, that energy, extra energy that we put in to make it vibrate more, is the heat there. So that's called conduction. When two objects are in contact, like a pot sitting on a stove, like if you put your hand on the stove out here, don't do that. If you if it's hot outside and heat is coming in through your windows, right? It's conducting through the window. All right. Convection is with liquids or gases, liquids and gases. Fluids would be a term that kind of takes care of both of those. Anything that flow. And if you look in a pot, you'll see little convection patterns, little, heat rises and falls back down. Cool water will come in to fill that. My grandparents had old radiators in their house, and big chunky iron things that look exactly like that. All right, haha. The heat from this thing would heat the air up here, and that air would rise, and cooler air would come in from underneath, and it made this little cycle where air would be warmed and rise and move through the room, and that convection pattern. Some of you may have a convection oven where there's a fan that moves that air around trying to heat the oven more evenly. Same idea. So that's the second means of heat transfer. The last one here would be radiation. And radiation, sometimes people think that's a scary word, but radiation means there's energy moving through space. So every time you turn on a light bulb, there is light energy moving through space. That's radiation. It's not dangerous. It's not harmful radiation. It doesn't have that much energy. But an X-ray machine would have harmful radiation. So you kind of got to, be careful with some of it. But light and right here, this eye of the stove is going to glow red, right? And that light is going to stream off of here, carrying energy. So you've got the conduction when two things are touching. You got the convection when fluids cycle because of heat rising and cooler materials coming in underneath. And you got the light, the radiation coming off from, we'll go with light here, okay? But all three of those carry energy, carry heat. This is an interesting picture here. Over on the left-hand side, they took a picture of a house and with a thermal camera, an infrared camera. You can buy one of these, but there was a big thing back in the 90s and 2000s. People would go around to your house and take pictures, and if you saw red right there, it meant that there was a whole lot of heat coming out of your house through your windows, through your doors, and the way to fix that would be to put a double pane window in. If you have two panes of glass with a little bit of air or some kind of gap between them, then it's a whole lot better insulator. So this is a before and an after. They put new windows in, they put a new door in, and they're saving a lot of heat. We moved here to Columbia, and our house had single pane windows, and we were very cold that first winter, and we spent a whole lot of heat money. I put new windows in, and it's helped a whole lot. So think about that. Even if you just take, plastic and put up over the inside of the window, the outside of the window, whatever, just kind of create a gap there with air. Air is a good insulator, and if you think about a sleeping bag or a blanket, you're making some space there between you and the cold, and then it's got to conduct all the way through. So even just taking a piece of plastic and just covering clear plastic, you can still see through it, the light still comes in, but put that on the inside. That'll save you a whole lot of money. There is a formula for that, for how fast heat comes through a material. We don't really need to worry about that. This is the thickness of the material, thickness of the piece of glass, how big the window is, the difference of temperature between the inside and the outside. And then, of course, there's a material that says this is glass, it's wood, it's insulation. You know, what kind of material are we talking about here? And there's an example up there, but you could put the numbers in on that. But let's not worry about that too much. I don't really need you to know that formula. Here's a good one, though. This is called the ideal gas law, and I've got two forms of it. Some of you have taken chemistry probably and seen this, and so the chemists kind of concentrate on this way, and the physics people are more interested in this. So it kind of depends on which one you're interested in. It's the same formula, but here you're talking about having some trapped gas. So here's a box, there's gas in it, and it's at a certain pressure and volume and temperature, and then things change. Maybe the temperature goes up. Well, that's going to change my pressure and my volume and my temperature over here. These three variables are all tied together. The volume, the pressure, and the temperature all work together. Now over here you had pressure and volume and temperature. This N is how many moles you have. And a mole is a way to count atoms or molecules. It's kind of like a dozen donuts, right? You've got 12, okay? Well, with 1 mole, you've got 6.022 times 10 to the 23 somethings, atoms, molecules, something, okay? So the chemist people are really interested in how many moles they have, and there's a constant that goes in there to fix all the units and the scale of the thing and stuff. The physics people really don't care. They say, well, I've got some trapped gas, and it's going to be like this, and maybe I add some heat, build a fire underneath it, and maybe it expands. So it started out volume 1, and here's volume 2. Because temperature 1, temperature 2 went up, maybe the pressure changes as well. Got the same number of atoms in there, same number of moles if you want to count it that way, but I had a change, and those three variables work together. So that's the ideal gas law. Now, one thing you got to be real careful about, this temperature right here, both of these temperatures and this guy all have to be in Kelvin. Okay, and that's one of those places where that other temperature scale is really important. Temperatures must be in Kelvin. All right, you will get the wrong number if you don't convert it to Kelvin. The pressure should also be an absolute pressure. You don't really need to worry about what that is, but it's not like what a gauge would read. It's including the atmospheric pressure as well. So that's the ideal gas law. I think it's good to see that and kind of be aware that there is such a thing. One thing, there it is right there, that little thing. We're going to talk about car engines and stuff in just a little bit, and that's a good place to think about the ideal gas law because you're adding heat and the volume is going up. It's pushing, the pressure pushes the piston down, all that. So we'll say more about that in just a second. This is an interesting formula here. We said that if you put energy into a material, that's a way to measure the heat, and the heat is tied in with the temperature. So Boltzmann came along here, this guy a long time ago, and he cooked up a formula that said the temperature is directly related to the kinetic energy, the average kinetic energy of one of these molecules. If you pick this guy and kind of followed him around, sometimes he's going to the right, sometimes the left, he's bouncing off the walls, he's bouncing off the other molecules in there. So his speed is changing, but on average, a single molecule would have this much kinetic energy based on the temperature of the room. And if I raise the temperature, if this number goes up, then my kinetic energy is going to go up. So the hotter it gets, the faster these things vibrate, the more room they need. They're going to bump into each other more, and that's where that thermal expansion comes in. Whether we're talking about, a bar of iron or a balloon full of helium, right? It's still the same thing. Now, one of the interesting things you can do is you say, well, shoot, I've already got a formula for kinetic energy, 1/2 mass velocity squared, right? And it's perfectly okay to put those together and to say, if I know the temperature of the room, I can tell you on average how fast a molecule is moving. And that's a pretty interesting calculation. You usually get something up around rifle bullet speed, like the bullet speed that a bullet comes out of a rifle barrel is basically how fast every molecule is moving in the room that you're sitting in right now. And those things are hitting you in the forehead and in the fingernail and stuff. They don't hurt because they're so small, so lightweight. But that's where air pressure comes from, because all of those things are pinging all the time on a pressure sensor, on your forehead, on the glass, whatever. And so that energy is kind of interesting to think about right there. When we talk about thermodynamics, there are 3 rules that I want to point to here. The first one is, believe it or not, called the zeroth law. What happened? They cooked up the first law and then the second law, and then somebody said, you know what, we should have started with this other thing. And so they said, well, we're going to have to call it the zeroth law now. 2 objects each in thermal equilibrium with a third object are in thermal equilibrium with each other. Maybe that doesn't seem worth making into a rule, but it's pretty important when we think about measurement of temperature and heat and all of that. It kind of provides a groundwork to begin measuring things. The first law is the one that's super duper important, and I've got a formula for that. There's no real formula for the zeroth or the second law, but this thing is immensely important when we're thinking about car engines and thermodynamics and how much work, W there is the work, that I can get out of heat, Q. And so what this is saying is that when I put heat into a car engine, when I put gasoline in there, some of it turns into work. Some of it pushes my car down the road, and the rest of it ends up right here as internal energy of the gas. It basically gets my engine hot. It basically goes out the exhaust pipe and doesn't do anything for me. This is the part that I want. I want to push my car down the road. I want the car engine to have a force over some distance and push my car as far as possible. So I put some gasoline in my car, I burn it, that makes heat, and I get some work. And I get a whole bunch of heat. For a car engine, unfortunately, about 25% of it goes into work, into pushing my car, and about 75% is heat. So that's not all that great. You put $4 of gas in your car, you only get $1 of motion out of it. So that's not all that great. One of the appeals of electric cars is that it's flip-flopped on this. About 75% of electricity that you put into the car goes into moving the car forward, and only 25% of it goes off as heat. LED light bulbs are a lot more efficient than incandescent light bulbs because they're not generating all that heat. But it's the same idea. I plug in a light bulb, some of it gives me what I want. With the light bulb, it'd be light, and the rest goes up in heat that I can't do anything with. And LEDs are a whole lot better than incandescent bulbs in that way. All right, down here the second law says it's impossible to construct a continuously operating engine that takes engine from a source and performs exactly that much work. Okay, you never get 100% efficiency. You're always going to have some loss. But here I'm losing 3/4 of my energy in a internal combustion car engine. So that's not all that great. It works, we do it, but maybe we'll have a better way someday. Okay. Here are some heat engines. A heat engine is any kind of machine that takes heat and it turns some of it into work. So this is a little toy steam engine. You can buy these little toys and you pull this out and there's a little brick of material that you put in there and light on fire, and that heat comes up in here and it boils some water, turns it to steam, and the steam goes through some pipes, There's a little steam engine right there, and the little thing goes and turns a tool. A long time ago, they had steam tractors and steam corn grinders and steam everything, all kind of steam engines on a farm, simply because that was all they had. Now we have gasoline engines. This might look like something that came out of your car if you have a 1971 Buick Skylark like I did. It looked a lot like that. Our cars now are kind of turned and a little bit different, but it's the same idea. Both of those are heat engines, and there's lots of different kinds of heat engines, but anything that takes heat and turns it into work, some of it into work, is a heat engine. Your car engine has 4 stages, 4 strokes here that it goes through. Here's that piston in the cylinder, and that creates a little space there where we can change the volume. The spark plug is right here. You got some valves, those open and close. The first stroke here is called the intake stroke, and the cylinder here is going to go, the piston here is going to go down, and this valve is going to open. You can see the little spring right there to hold it closed, to pull it up tight so nothing gets in or out. But a little thing comes along and bumps it right here, and that opens this up, and it sucks in oxygen, air, and gasoline, and then the little door closes like that. And so that first stroke is the intake stroke. It brings in some gas and some air, and it's going to burn that gas and air. I need to compress that gas there, so that it's heats it up, and so that it's ready to burn when the spark plug goes zap. So the second stroke would be this thing going up like that, and when I've got that gas compressed really tight there, right at the top of the cylinder, and packed it down about as small as it can get. Both doors are closed, so nothing can escape. But there's a little spark of electricity bzzz, right there, and that ignites that gasoline, and this all burns, which creates a tremendous amount of heat, which creates pressure. And that's going to push the piston back down in what we call the combustion stroke, or I like power stroke better. And that's the part that's driving your car. This thing's attached to a thing that goes like this, and then you've got gears attached, and it all turns. It's going to turn the wheels of your car, okay? So that power stroke takes care of that. Now I've got all that burnt gas in there, so I need to have one more stroke, and this door is going to open up, that valve, and all that exhaust is going to go into your tailpipe and out the back of your car, carrying with it a whole lot of heat that I can't do anything with, and I'm just throwing it away and warming up the planet at the same time. So that's what you've got there. Perfect place to think about thermodynamics, because inside this cylinder we have pressure and we have volume. You can see the volume is changing there, right? And the volume gets bigger, and I suck in some air. The volume gets smaller. I compress the gas. The volume gets bigger because the pressure is pushing it down. Pressure is coming from the heat, and so the temperature there is an important factor. And then I dump it all out, and those 3 variables are all tied together: pressure, volume, and temperature. The ideal gas law is going on, that says how big it's going to be, how much pressure, what's the volume, what's the temperature, all that. And I've also got that first law of thermodynamics, which says that you've got some heat going in there, and some of that's going to turn into work, which pushes my car. So that's kind of where thermodynamics gets us. Here's some graphs, and you don't need to know all these terms, but you just might want to know that there's a isothermal expansion. That's where I've got that heat. Here's the hot part right here, and that's going into the cylinder. That's the burning gasoline, and it expands this thing up, and then it continues expanding in what we call an adiabatic expansion. Adiabatic means I'm not adding any heat, so that's after the fire's burned out, but it still continues to go up a little bit. And then there's an isothermal compression, where I have, at the same temperature, I'm I'm compressing this back down, and then there's an adiabatic where I'm not adding heat, and I continue compressing that. That would be compressing that gas so it's ready to burn. Right here I burn it, the cylinder expands, and then I compress it back down. There's all kind of little graphs. A lot of times we put the pressure on this axis and the volume on this axis, and when you draw all four of those thermodynamic processes there, you get this shape, and the work that you get out of an engine is this area inside the curve right there. And you can measure that with calculus. We don't need to worry about that. But that space inside there is a measure of the work. So I'll just put area equals work, and we want to see how much work. Obviously, if it's going between here and there, potentially the area, and I can't draw a straight line today to save my life, the area could be something like that, right? If I could get this thing to go in square straight lines instead of these funny curves here, I'm only getting a small part of that possible work there, and that's what we refer to as the efficiency of a heat engine. Efficiency, not sure that's spelled right. You've got heat. Heat is going to go from hot to cold. So this is the burning inside your gasoline, inside the engine of your car. Out here is the outside air. And as that heat goes from hot to cold, some of it can get diverted off here into work. And so you've got a diagram. You see the little 4 stages right there. That yellow circle represents the heat engine, which is this process. It's a cycle. It just keeps going around and around and around. Your engine goes through that cycle 3,000, 4,000 times a minute. You can look at the RPM gauge and see how fast it's going. But it just keeps doing that thing over and over. We get a little bit of work out of each cycle, and together it pushes our car down the road. Okay, and don't look at that because that's not even the right stuff. That's kinematics. I didn't change it. But that's what you need to know about thermodynamics. It's really interesting stuff. We've barely dipped our toe in it today, but that's what I would like you to know about it. So thanks for stopping by, and have a great day. Let me know what I can do to help.